20 grams per ton. That is the contamination limit for furnace-ready cullet. If a batch exceeds this limit, roughly the weight of a single AA battery in 1,000 kilograms of glass, the entire lot is rejected. Why? Because ceramic contaminants do not liquefy at furnace temperatures. They survive the melt as solid inclusions called stones. When the new bottle cools, the glass contracts around this inclusion. The stone acts as a stress concentrator. Under pressure, the container fails. To hit that 20-gram target, the line must execute a precise mechanical sequence: drying, sizing, aerolic separation, and optical ejection in free fall. Here is the engineering behind the closed-loop glass line. The feedstock arrives as raw cullet. It is a chaotic aggregate of container glass, organics, paper, plastics, and structural contaminants. But before we can sort, we must condition the material. A critical, often overlooked variable is moisture. If the glass is wet from rain or organic residue, fine particles like sand and paper dust adhere to the surface of clear shards. The optical sensors downstream operate on light transmission. If a clear shard is coated in wet dust, the sensor will misread it as opaque trash and eject valid glass. Therefore, in high-end facilities, the first stage involves industrial drying tunnels or high-velocity air knives to strip moisture and ensure the material is free-flowing and optically clear. Once dry, the material enters the comminution stage, the impact crusher. Unlike jaw crushers used in mining, which rely on compression, this unit uses kinetic energy. A high-speed rotor throws the glass against wear plates. The goal is not just to break the glass, but to liberate it from caps, rings, and labels. The output target is a specific particle size distribution, typically between 15 and 50 millimeters. This size window is a critical constraint for two reasons. First, optical efficiency. If shards are too large, they can physically mask contaminants. A metal screw could hide underneath a large curved piece of glass on the conveyor belt. Second, furnace thermodynamics. If the shards are pulverized into dust, known as fines, they become a liability. In the furnace, fines melt too rapidly compared to the larger cullet. This uneven melting rate creates seeds, microscopic air bubbles trapped in the final glass. Furthermore, glass dust is abrasive and lightweight. It gets sucked into the furnace exhaust system, clogging the regenerative filters. To prevent this, vibratory sizing screens immediately filter out undersized material. Gravity is the filter here. The stream passes through a unit known as a zigzag sifter, or air classifier. A precise updraft of air is blown through the falling curtain of glass. The physics rely on the drag-to-mass ratio. The glass shards are dense and aerodynamic. They overcome the airflow and fall straight through. The paper and plastics have a high surface area relative to their mass. The aerodynamic drag overcomes gravity, sucking the light material upward into a cyclone filter. The constraint here is air velocity control. With the organics removed, we tackle the metals. First, ferrous metals. An overband electromagnet is suspended above the conveyor. The magnetic flux density is calibrated to lift steel caps and jar lids against gravity, pulling them out of the material stream while the glass remains on the belt. The harder challenge is non-ferrous metal, aluminum, lead, and copper. The stream passes over an eddy-current separator. A high-speed magnetic rotor spins inside a non-conductive drum at thousands of RPM. This changing magnetic field induces an electrical current, an eddy current, inside conductive metals like aluminum. According to Lenz's law, this induced current creates its own magnetic field that opposes the source. The result is a physical repulsion force. The aluminum is kicked off the belt trajectory into a separate bin, while the non-conductive glass falls vertically. This system has a major failure mode, shielding. If the material layer on the conveyor is too thick, a piece of aluminum might be buried under heavy glass shards. The magnetic repulsion force is not strong enough to lift the metal through the weight of the glass covering it. To prevent this, vibratory feeders must spread the material into a strict monolayer, a single layer of shards with no overlap, before it hits the separation zone. The glass is now mechanically clean, but it contains the critical enemy: CSP, ceramics, stones, and porcelain. To the human eye, a piece of white ceramic looks identical to a piece of frosted or labeled glass. To the furnace, they are opposites. The shards are accelerated off the end of a stabilization belt into a stable freefall trajectory. For a fraction of a second, the glass is airborne. In this flight window, the material is scanned by a complex sensor array. Standard cameras analyze opacity. A backlight blasts through the stream. Valid glass transmits light. Ceramics block it. But cameras have a blind spot. Materials like leaded glass or heat-resistant cookware, like Pyrex, are transparent, just like bottles. However, they have much higher melting points and will cause furnace inclusions. To detect these, advanced lines use X-ray fluorescence or X-ray transmission sensors. These sensors do not look at color, they look at atomic density. Lead and heat-resistant glass have a higher material density than soda-lime container glass. The X-ray sensor detects this density delta and flags the transparent shard as a contaminant. The cameras analyze spectral signatures. In a typical cascade setup, the first pass ejects all amber. The second pass ejects all green. The remaining stream is flint. This makes clear glass the hardest product stream to manage. It requires the highest number of ejection events, meaning it has the highest risk of cross-contamination if the machine calibration drifts. Before the cullet leaves the facility, it hits the final gate, quality control. Automated sampling systems pull a statistical fraction of the output, for example, 10 kilograms every 30 minutes. This sample is analyzed for CSP content. The industry tolerance is brutal. As mentioned, the limit is often less than 20 grams of CSP per ton of cullet. If the sample exceeds this limit, the logic dictates that the sorting parameters have drifted, the silos are locked, and the production lot is flagged for reprocessing. This is the proof moment, ensuring the furnace-ready claim is valid. The processed material is transported to the glass manufacturing plant and mixed with raw batch materials, sand, soda ash, and limestone. Here is the thermodynamic advantage. Virgin silica sand has a melting point of over 1,700 degrees Celsius and requires massive energy input to undergo the phase change from solid to liquid. Cullet acts as a thermal catalyst. Because it has already been melted once, its glassy structure is established. When introduced to the furnace, it liquefies at a lower temperature, creating a molten bath that helps dissolve the harder-to-melt sand and soda ash. This reaction is non-linear. Industry data indicates that for every 10% of cullet introduced to the batch, furnace energy consumption drops by roughly 2 to 3%. Furthermore, using cullet prevents the chemical release of CO2 that occurs when raw soda ash and limestone decompose. Because glass is an amorphous solid that does not degrade on a molecular level during melting, the cycle is theoretically infinite. A bottle can be recycled 10 times or 10,000 times without losing structural integrity or clarity. The limit of recycling is not the material itself, it is the precision of the separation window. This was an analysis of cullet processing logic. For more breakdowns on industrial separation and material science, check the archive.